let's continue. Okay, so part D. What is the gravitational pull of the Earth on the hammer at the top of the arc? Assume the radius of the Earth is 6.40 times 10 to the 6 meters from the base of the cliff. The mass of the Earth is 6 times by 10 to the 24 kilograms. Okay, let's make a list of what we know. So, we know, let's scoot this up a little bit. Okay. We know that the radius of the Earth is 6.40 times by 10 to the 6 meters. We know that the mass of the Earth is 6.00 times by 10 to the 24 kilograms. We know the mass of the hammer is 60 kilograms. Also, something to keep in mind, it's asking what the gravitational pull of the Earth on the hammer is at the top of the arc. So that means from the center to the edge of the Earth is that 6.04 times by 10 to the 6 meters. So we need to add this extra little bit of height in. So this is not just going to be the radius of the Earth, it's going to be that plus that height, the 1,023.95 meters. That will be our overall radius between the center of mass of the two objects. And then we have a gravitational constant that we'll be using, 6.674 times by 10 to the negative 11 Newton meters squared per kilogram squared. Okay. Alright, awesome. Now, gravitational pull, our main gravity equation between two objects is that force due to gravity is equal to that gravitational constant, mass of the one object, which is Earth, mass of the second object, which is the hammer, and then the distance between their center of masses squared. Okay. And again, I've made my list, and so I don't need to, it asks what is that gravitational pull, so I'm solving for that gravitational pull, that force due to gravity. And the equation's already rearranged to solve for that, so I don't need to rearrange the equation. If you're not going to write the numbers in to the equation, you need to make a list of them. And I would prefer it laid out that way. Keep everything symbolic, solve for everything symbolically over here, but then just give me your list so that I recognize you know what G is, what the masses are, and the distance between them. Okay, so take a moment, plug that in your calculator. And the long answer that I got was 586.394 newtons, which is about, for 3 sig figs, 586 newtons. Okay, let's continue. Next, part E. If Thor's hammer has a charge of 2.50 times 10 to the negative 8 coulombs, what is the electrical force between the hammer at the top of the arc again and a cloud that is 2,500 meters above the base of the cliff? The cloud has a charge of 5 coulombs. Alright, let's make a list of what we know, what we don't know. So, first, the charge of the hammer. Okay, charge, which you usually represent with the letter Q, of the hammer, 2.50 times by 10 to the negative 8 coulombs. And then what else do we got? What is the electrical force? What is that? Force electric between the hammer at the top of the arc and a cloud that is 25 meters above the base of the cliff. Let me draw you a picture of this really quick. We have this cliff. We have the hammer that flew. Here's the base of the cliff. I'll be 0. And 2,500 meters above that base, there's a cloud. Okay? Now we know at the top of the arc that the hammer traveled 1,023.95 meters. And so if the hammer is here and the cloud is there, and those are my two objects, the distance between them is not 2,500 meters, it's not 1,023.95 meters. It has to be the difference between the two, right? The distance between them would be right there. So that R value, that distance between them, would have to be the 2,500 meters minus the 1,023 meters. Okay, what else do we know? It says the cloud has a charge, so charge of the cloud would be 5 coulombs. And then we have a constant here as well. Let's see, I wrote that down. Yeah. This coulombs constant, 8.9875 times by 10 to the 9th Newton meter squared per coulomb squared. Okay, the equation for force electric is equal to K, Q1, which is our hammer, Q2, which is the cloud, divided by the distance between them, squared. It's very similar to our gravitational attraction equation. And it's rearranged, it's already solved for what I'm looking for. I know everything else. I've made a list of it, and my knowns and my unknowns here. And so I'm just going to be plugging those numbers into the equation. Common mistake is forgetting the squared, so be mindful of that, and keeping everything on the top of the fraction and the bottom of the fraction. So again, part of your practice should be plugging this in your calculator. So take a moment, do that, and then come back and let's talk about that final answer. Because when I plugged in those numbers, I got a long final answer of 5.15638 times by 10 to the negative 4 newtons, because this is a force, which is about, for significant figures, 3 sig figs, 5.1, and this will round up to 6 times by 10 to the negative 4 newtons. Okay, great. That was part E. And then we have part F. How long was the hammer in flight before it hit the ground? Okay, there's two things going on here. Actually, this is a good picture of it. We have the time it took for the hammer to get this far, and then the time it took for the hammer to get that far, right? So I'm going to label this at the first, and this one's going to be the second, okay? We have more information for the y direction right now, and so that's what I'm going to use. I'm going to use the y direction to solve for my time, both of the first part and then the second part. So for this first part here, y initial was the 70 meters. We talked about that. Y final was 0. We solved for that. That was the 1,023.95 meters. Velocity initial in the y is the 400 sine 20 meters per second. Velocity final is equal to 0. Acceleration is due to gravity, negative 9.81. And then we are solving for that time of part 1. That's what we want to know. All right, a couple things. So I walked through kind of where I got each of these values in part B. So if you need to go back to to that video and watch those if you're wondering where did these numbers come from. Okay, and we need to pick an equation that contains time, because that's what we're solving for. We know everything else. Then so it's probably a matter of picking the one that looks the most simple to us. And so when I look at my list of kinematic equations, one of them is velocity final equals velocity initial plus acceleration multiplied by time. Okay. This is nice because this one's 0. And then I'm going to solve for time. So this is multiplied, so I'll wait. This whole thing is added, so I'll start there. I'll subtract that to the other side. Now I will divide by that acceleration, and that will tell me time 1. So I'll take the negative of this and then divide it by my negative acceleration, so those will cancel. As far as negative sign goes, that leaves me with a positive time. That's good, that makes sense. I plug that into my calculator and I get a time of 13.9458 seconds. And I'm not rounding for sig figs yet because that's not my final answer, that's just the time of the first part here. Okay, now the time of the second part, I'm going to make a new list. For the second part, my y initial, I'm starting at the top of the arc. So that would be initially 1,023.95 meters. My y final of the second part is going to be the ground, be 0 meters. Velocity initial in the y, well, at the top of the arc, that velocity was 0 meters per second. I do not know this velocity at which it will hit the ground, but I do know the acceleration is still due to gravity, and that I have to figure out this second time part of part 2. Okay? So I need to pick an equation that I know everything except for my unknown, so it cannot contain velocity final because I don't know what that is. Okay, so the equation that does not have velocity final is that third one. It's our longer one. It's the, I wonder if I'll be able to write it all in here. It is the y final equals y initial plus velocity initial in the y multiplied by time plus 1/2 acceleration in the y time squared, and this is of our second half. Okay, let's see if any of these are 0. So let's see, y final, that's 0. Velocity initial, that one's 0. And anything multiplied by 0 is 0, so that whole thing will drop out. So we're left with 0 y initial plus 1/2 acceleration t squared. I'm going to subtract y initial, so I'll have negative y initial equals all of that. I'll divide by the 1/2 in the acceleration. And then I'll take the square root of both sides. So our second time will be negative y initial divided by 1/2 acceleration in the y. Something that I do to help recognize, parentheses, all that, I don't plug this in as 1 divided by 2. I just plug it in as a 0.5. So that clears up a set of parentheses that we don't necessarily have to work with. And then multiplied by negative numbers, so those negative signs will cancel again. And we are left with, when I plug all that in, get a final answer of time 2 being 14.4484 seconds. Something common mistake I see a lot is students just telling me what this number is but not showing me how they got it, so be mindful of that. And so the total time would be time 1, so time total would be time 1 plus time 2. This plus that, and that is 28.3942 seconds which 3 sig figs is about 28.5